This is a bonus video about something called exact sequences. There aren't any homework problems or exams about this. This is just, there's a very nice way to summarize all of the vector operations that happen in Calculus 3, and it turns out that in a whole bunch of other mathematics, exact sequences end up being like a nice way to summarize information. Is this specific way of writing things likely to show up in a physics or engineering class? Probably not. Are you curious what's going on with this weird picture? If so, then, I don't know, watch this and see what's going on. So, this weird thing that's supposedly a summary of what's going on with all the vector operations in Calculus 3 is called an exact sequence. I'll start by telling you what an exact sequence is. Then I'll show you like the simple exact sequence. It's called a short exact sequence that you learned in Calculus 1 without noticing that you learned it. And then I'll tell you how this definition of an exact sequence helps you like keep a bunch of little information all organized into one piece, into one like package. Okay, so what is an exact sequence? An exact sequence is a series of, well, I'm not going to use the like fully proper mathematical terms for these things, but up above here, like this C infinity R3 R3, those are all the vector fields in 3 dimensions. So I'm going to have like, well, here's some vector fields in 3 dimensions. Here's some functions on space. Here's some functions on space again. What are those, like, what kind of thing is that? I'm just going to say that they're sets of objects and operations that go from one set to the next. Oops. One set to the next. And they satisfy 2 properties. The first one is that if you start somewhere and you do 2 operations in a row, you land on 0. So up here, I've got like functions from space, like functions on space. There is a function on space that just gives you 0 everywhere. And then there's a vector field up there, 3D vector field. There is the 3D vector field that's just 0 everywhere. That's just, there's no wind. That's a vector field. If you do 2 operations in a row, you get 0. The second rule is that if you do 1 operation and get 0, then you came from the previous operation. Even if you didn't know it. This essentially says that if you do 2 operations in a row, you get 0, and also 2 operations in a row is the only way to get 0. I'll summarize these in a little box that goes above my head here, hopefully, if I did it right. Yep, 2 operations in a row gives you 0, and if you get 0 from an operation, you came from the previous one. This is what an exact sequence is. This is the definition of an exact sequence. It seems kind of weird, so let me show you the one that you've already learned without knowing it, and then I'll show you how these rules apply to gradient, curl, and divergence. Okay, so from Calc 1, here's an exact sequence that you learned in Calc 1. I have to tell you how to get between various things, and the way that you get from, oh wait, that's not right. the way that you get between these different, like what are these objects and how do you get between them? So R, this is the real numbers. So this R represents the set of all the real numbers. And this arrow says, hey, if you start with literal 0 and you follow this arrow, it means you go from 0 and now you land in the real numbers on 0 in the real numbers. This thing is functions, one variable functions. And here it is again. So like y equals x squared is in here. Y equals sine x is in here. It's not just one variable functions. This infinity, C infinity, means that it has infinitely many continuous continuous derivatives. So this is the one variable smooth functions. No absolute value of x is invited. Well, if you have a real number, following this arrow means you're supposed to take the real number, like 6, and turn it into a function. Is there a function called 6? Yes, it's just the function y equals 6. So this is just 0 sitting by itself. You could take 0 and land in the real numbers. And then you could take any real number and make a function that's just y equals that real number. The last arrow that I have to tell you what to do is this one. This is the derivative of the function. So if you take a one variable function, like y equals x squared, you can take the derivative of the function and you land on a new function, like y equals 2x. Okay, why is this an exact sequence? This is exact. Sure. The reason this is an exact sequence is, first of all, we have to check the first thing. The first thing says, if you do 2 arrows in a row, you land in 0. So let's check it. If you start at 0 and you go along here, then you land on the real number 0. And then if you follow this arrow, you get a function 0. That worked. We landed on 0. Okay, let's try starting here. If you start with a real number, like let's say 7, you go and you follow this arrow, you get the function 7, like the function y equals 7. Then you follow this arrow is take the derivative. Yeah, the derivative of this constant is the function 0. So like no matter where we started so far, if we started here or if we started here, when I did 2 arrows in a row, I landed on 0. Well, what about here? If you start with some weird function, like y equals, I don't know, x to the 10th, and you take the derivative, and you go a second operation, well, this operation says, just go to 0. Okay, so that one works for free. So this was the first operation, or the first requirement to be an exact sequence. It says if you follow 2 arrows, you land on 0. And it happened every time. When we took 2 trips, like 2 arrows, we landed on 0. Okay, that's the first requirement. What's the second requirement? The second requirement is that if you ever land on 0, it means that you came from another arrow. So let's see it. Sorry, my erasing game is not great. Let's say that you took a function, f of x, and you took this arrow and you landed on the function 0. How could that ever happen? What kinds of functions have a derivative that equals 0? The answer is those are constant functions. So what the second can't spell. What the second requirement of being an exact sequence is that if you ever take any object and you land on 0 when you go forward, that means that there was a way to go backward and find something that it came from. In this case, since this was a constant function, yeah, that constant function is chilling over here in the real numbers. So this must be a constant, like the function is a constant a. And so that means, well, yeah, you look back here and you find that, yep, the constant is right here. So these are the 2 requirements. Take 2 steps, you land on 0. And if you take 1 step and land on 0, it means you came from somewhere before. So this is the Calc 1 exact sequence. The Calc 1 exact sequence is not worth ever telling you as is an exact sequence, because it's like too much machinery for no payoff. The Calc 3 exact sequence is worth it, in my opinion. So I'll show it to you now. So here's the Calc 3 exact sequence. Here's some real numbers. Here is functions that are defined on space. So this is each point in space has a number assigned to it. Your prototypical example of this is like functions that tell you at each point in space what the temperature is. The temperature function in space is one of these things. That's like C infinity from R3 to R. These things are 2 copies of the same object. These are vector fields in 3 dimensions. And then this one is back to functions again. What are the operations? Well, this one says if you start with a real number, just turn it into a function. Like if you have the real number 8, this can be the function. The whole world is 8 degrees. If you have a function, what you can do with it to get to the next spot is you can take the gradient of the function. If you take the gradient of a function, you get a vector field. If you have a vector field, you can take the curl of the vector field and it gives you another vector field. And if you have a vector field, you could also take its divergence, and the divergence, it does the dot product, so it's not vectors anymore. You get a function. The claim here, and like the key claim that like combines a whole bunch of vector calculus facts into one fact, is to say this is an exact sequence. When you say this is an exact sequence, you're saying a whole bunch of crazy stuff. In particular, if you just look at requirement number 1, it says that if you ever take 2 operations in a row, you get 0. Well, what does that mean? It means, for the first one, if you take a real number and take the gradient of that real number, you get 0. So that says the gradient of a constant function is 0. That's true. The gradient of a constant function. Like if it's 12 degrees everywhere, that's our constant function, and you ask, which way do I go to make the temperature increase the fastest? That's the gradient. The gradient is like, I don't know, it's 12 degrees everywhere. And the gradient just hands you 0, 0, 0. Okay, that's these 2 arrows in a row. The exact sequence says you can follow any 2 arrows in a row. So like, what about these 2? These 2 say that if you take a function and you take its gradient and then you take the curl of that, you get 0. This is a fact that got like almost a whole section about it. It says that the curl of a conservative vector field is 0. What about the next 2? The next 2 says, well, if you take the curl of a vector field and then its divergence, you get 0. And that was a fact that we said in this class also. It's that divergence, that div curl f is 0. The other way we wrote it was that curl f is source free. I think we do this in section 17.5. What about the last 2? Oh, the last 2 just say that if you turn something into 0, then it's 0. Okay, so that's not so interesting. But these 3 facts are like big facts in chapter 17, and they're all written in this exact sequence. That's just number 1. Number 2 says if you ever get 0, that means that like you have secret knowledge that you came from somewhere. So what about this one? If you take the gradient of a function and it equals 0, that means that the function actually came from the previous slot. So the gradient of a function equals 0 means that the function is actually a constant function. This is like the Calc 1 fact, that if the derivative of a function is 0, then the function is a constant function. Here, it's if the gradient of a function is 0, the function is a constant function, and that's true. What about here? If you start here, and you say, well, what if I got what if the curl of a vector field is 0? Well, if the curl of a vector field is 0, then apparently it came from the gradient. And this was our conservative vector field test. It said, you want to know if a vector field is conservative? Do you want to know if you came from somewhere? Then take the curl and see if it's 0. So the way to write this in like physics terms, I guess, would be that curl f is 0 only for conservative f. Finally, if you take the divergence of a vector field and you get 0, it must have come from the curl. I don't know, G. So if your vector field has no source, it's source-free, then that means it's the curl of some other vector field. And I think that was a smaller fact. It's not nearly as big of a deal. The reason these ones are a big deal are because they have the word conservative in them, which lets you talk about a potential function, and like those are big physics ideas. But anyway, all these facts we teach generally as like separate facts that if you take the curl of the gradient, you get 0. If you take the gradient of a constant, you get 0. If you take the divergence of the curl, you get 0. If you piece all those together, you get to say it, if you like learn this word, you get to say it as one big fancy math fact, which is this sequence is exact. Okay, will you ever have to say this? Like, will you ever have to like prove that you know this to anybody? Probably not. But if you find yourself in a situation where you need to remember, like, wait, which things are 0? There's like all this curl and div, and especially if you start writing curl as del cross. So like you have curl of divergence of f is 0. And so here's curl is del cross. And divergence is del dot. Like, how am I supposed to remember that del cross del f is 0 and del dot del cross? Like, oh my gosh. And why are these f's different sizes? If you need to remember all those things, what you can do is just like write down that, well, if you do grad curl div, if you do any 2 of those in a row, you get 0. And that's this one fact. Yeah, it's just a bonus fact. It's not a big deal. There's no homework problems about it, but it's just pretty cool. And it's a nice picture that summarizes all of our vector operations into one. So I hope you enjoyed. It's just amusing.